Okay, hello everyone. Welcome to the first part of the fifth lecture, where we still talk a little bit about difference and difference estimation before coming to the regression discontinuity design in the second part of the lecture. Okay, in the last tutorial, we already talked a little bit about potential tests of the difference and difference design. Yeah, so for instance, you remember that we need the parallel or common trends assumption, and well, we have to kind of try to make it plausible. As we said, this assumption is intrinsically non-testable because it refers to the counterfactual, which we cannot observe. Now, if we happen to find non-parallel trends before the treatment even takes place, then of course it is pretty unreasonable to assume that after the treatment takes place, the trends would have been parallel in a world where the treatment did not happen. If we see that two groups are completely moving in different trends in different directions, then it's it's a wide stretch to assume that one group is a good control for the other. Yeah, so kind of therefore, we kind of try to test the parallel trends assumption by this kind of Granger type causality test. Yeah, so this refers to the Granger causality that kind of like something gives you like one time series gives you information about what will happen in another time series. Yeah, it's not really a causation, but it's type of a Granger causation. Yeah, that's kind of like a different concept taken from time series. And what we do is that we simply check whether the treatment has an effect before it even takes place. So kind of actually what we're doing is precisely that, right? Kind of like if the lines move in parallel before the treatment takes place, that means kind of like the treatment does not have any effect, meaning that the treatment group does not behave differently from the control group before the treatment takes place. But if the lines kind of move a bit in parallel, and then we find one instance where kind of like they kind of go completely apart, this is kind of like an instance where we see something that the treatment has an effect. Really, what that actually means is that the treatment group behaves differently before the treatment than the control group. Yeah, so kind of if we see that there is a significant difference of the behavior before the treatment takes place, then we say, well, the parallel trends assumption is probably not plausible. Yeah, so how do we do this? We have like t+1 time periods, and like t is the reference period or base period, as it's also called, and we have a post-treatment period. Yeah, so that's kind of like the only period where the treatment has taken place. And what we're doing is that we use the typical two-way fixed effect structure, including some vector of observed covariates. And here, this is kind of where the magic happens. You see that kind of like we have a sum where we allow for beta L to depend on the time period. And DGL is simply basically a dummy that tells you whether a unit in group G is treated in time period L. So kind of that dummy here is one if the unit is in the treatment group and the time period happens to be a time period L. So for instance, if kind of L is equal to 2, then this dummy will be 2 for everyone. This dummy will be 1 for everyone that is in the treatment group in time period 2 and 0 otherwise. Yeah, so using this specification, we can actually measure the effect of the treatment in time period L on the treatment group. And the beta t+1 is actually our treatment effect. Yeah, so kind of like when we did the usual treatment effect, two-way fixed effect specification, we did not have the summation here. There was only one beta, and that referred to the post-treatment period. And now we have betas that also refer to the pre-treatment periods. Now, as I said, kind of if we really have parallel trends before the treatment takes place, then we expect that all the betas are 0, because there is no, all the betas being 0, that really means like the lines move in parallel. Okay, so what would we do? Well, we would simply estimate this model. We get the estimates for all the betas. And then we can, for instance, do a t-test. So kind of, an f-test. Yeah, we kind of test whether all the pre-treatment betas are jointly 0. And if we reject that, we know that, well, there is some beta where there is like a difference in trends between the both groups. Now, what people normally do in practice is that they test each beta individually. Yeah, so kind of you do a t-test on each beta individually. Now, there's of course like, but it sort of makes a bit of sense, right? Kind of if you find that the betas are significantly different from zero, then you know that the groups differ somewhat in one of the pre-treatment periods, which makes the common trends procedure assumption implausible. However, kind of, first of all, if you do the individual t-tests and not the f-test, that means that you're basically, your overall test will not maintain its level alpha, right? So kind of like when you want to kind of reject the null hypothesis at 5% of all cases, you should actually use an f-test and not individual t-tests, which have each a 5% chance of, falsely rejecting the null. Yeah, so that's one criticism. And then the other criticism is, of course, that we may make an error of type 2, right? So kind of there is a difference in trends before the treatment. However, we are unable to find that, right? We are unable to reject the null hypothesis because, for instance, our data is too bad. Yeah, and so somehow there is like bad incentives here. So kind of like you want to have noisy, bad data in the pre-treatment period so that you cannot reject this thing. Because if you reject, well, you cannot write a difference paper. Yeah. So kind of when you want to publish your diff paper, you should better find something where the common trends assumption holds. Yeah? So kind of people want to fail to reject this null hypothesis. And then in the post-treatment period, you want to have really nice data because there you want to have something really significant. Yeah, so this kind of creates bad incentives somewhat, and this can kind of make the publication bias worse. Yeah, so that only things that are really get a nice, significant, strong effect are published. But of course, right, there's a selection of papers that get published because of that. And therefore they do not represent the actual relationship that we have in the population. And so that's called publication bias because we have a selection of results that get published and the results are therefore not representative of all the results that could have been obtained. Okay, so that's kind of like the typical tests that people do. Then there's various extensions of the different diff idea. Yeah, so for instance, like right now we had like differences between two groups, then we can actually extend that to have like, a triple different diff. So for instance, like that's our example here, we have a kind of a change in healthcare policy, yeah, and that affects only people that are at least 65 years old. And this change in healthcare policy only happens in state B. Yeah, so we have some change in the policy and we kind of measure our outcome variable, which is some measure of health, whatever, right? Okay, so now what kind of possibilities do we have? Well, as usual, right, we can simply try to find a good control group within state B. And we could kind of look at younger people. And we take the young people as a control group for the old people. But of course, it's very clear that like the health of the elderly may develop very differently from the health of the younger. So kind of, it's not a good control group. That's hopefully very clear. Moreover, you could kind of take the same group, like the elderly, people older than 65, in another state. So for instance, a state that is your neighbor, where the policy change did not happen. However, we again have this issue that maybe there's state-specific effects. So for instance, there may be income and wealth differences between the two states. And therefore, there may also be, again, different trends in terms of the health outcome generally between state A and state B. Therefore, the common trends assumption would not hold. Okay, so what do we do? Now, what we could do, we could try a different diff strategy, right? So kind of, let's say, oh no, this is not different diff yet. Yeah, so we can also kind of compare the elderly in state B after the treatment with the elderly in state B before the treatment. Yeah, so now, again, this is kind of the final possibility, but we have time effects that can bias the results. Yeah, so kind of course, we had this, shocks to the economy that happens between the before and the post-treatment period. Those things may bias the results. in this case, maybe think of, I don't know, maybe some atomic plant exploding in between. You know? So, and if you do this comparison here, all the people dying afterwards would maybe be kind of attributed to the health, you know, outcome, to the health policy, if you don't account for this time shock. You know? Okay, now these are the single differences that we already saw in the diff and diff discussion that typically don't work. So let's try actually differences. Yeah, so for instance, what we do here is that we take the elderly after treatment in state B versus the elderly before treatment, and we compare that with the non-elderly, the same thing, right? Post and before treatment, and everything is done in state B. Yeah, so, okay, now this thing would be consistent if like the average health in the elderly group develops over time in the same way as the average health in the non-elderly group. Yeah, so kind of we need the common trends. In a world where the health policy change did not happen, these groups have to move in parallel. However, it's unlikely to be true. Like the health trends in the group of the elderly is very likely to be different over time than the health trend in the younger population, right? So let's do this kind of like the same thing in state A, right? So again, here we do the same thing. Yeah, that's just another different diff estimator. So post-treatment versus pre-treatment in the elderly group. And here again, post-treatment versus pre-treatment in the younger group. Yeah, so another different diff estimator now referring to state A, which is our control. Okay, so again, we are likely to find something that is non-zero. So you see kind of when this, actually, if the parallel trends assumption were to hold, this thing here, this diff and diff estimator should be close to zero because there has been no treatment in state A, right? Yeah, so we should find something that is close to zero. However, in this case, because the trends between the elderly and the non-elderly are different, we will find something that is probably not zero, right? And this something is actually important for us. Yeah, so let's say the trend difference in state A between the elderly and the non-elderly is similar, comparable to the trend difference in state B between the elderly and the non-elderly. We can again get a consistent estimator by basically canceling this out. We take a difference between the two difference and difference estimators. Yeah, so basically, that's actually what you see here, right? So kind of this is the first diff and diff estimator, the first thing kind of, and here we have the second diff and diff estimator. And when we take the difference of both, we kind of cancel out these differences in trends between the elderly and the non-elderly, yeah? And again, we can write this as a regression model. You see here, and it simply gets a little bit more complicated. So you see kind of now this new regression models has to contain dummies for the state, for the time periods, for the group, and all the interactions. And then the final coefficient that we are interested in is this triple interaction. Yeah, so this thing here is a dummy variable that is only one if we are in the post-treatment period in the treated state and we are in the treated group, in the elderly group. Yeah? And it can be shown that again, this, if you run the regression, the estimate will be this difference in difference and differences. So this triple difference estimator. Yeah. Okay. So you see, kind of, we can simply extend the diff and diff idea to kind of, let's say, more complicated setups. Well, you could apply the same thing to quadruple differences if you find a good application for that. So that's one extension. And then we also mentioned a little bit kind of like synthetic control methods in the last tutorial, which has been hugely influential. Yeah? So kind of like Abadie is in every paper that is kind of on the synthetic control. So he's really the driving force. That's at least the impression that you get when you read the literature. And okay, so what was again the synthetic control? Many times you have actually multiple potential control groups. Yeah, so for instance, look at the states of the US. That's actually the examples that they consider. For instance, you have California changes a policy. Then in principle, you have 50 states that you can use as a control group. Now, it is not clear which other state would be best as a control group. Would it be Texas? Well, Texas is also pretty hot, but it's very different in terms of like the political spectrum versus California. Should it be New York? Well, New York is closer like in terms of politics, but it's also at the other end of the world, right? It's kind of at the other coast. So it's not clear which group is the best control. Now, what the synthetic control method does, it takes all the 50 states, yeah, and it kind of combines them. And instead of a real control group, you then have a synthetic control group, yeah, which is a combination of the potential 50 states that are the potential control groups. And it does this by matching on the observed covariates and on the observed outcome variables. Yeah, and it turns out that the synthetic control now resembles the treatment group much more closely than the kind of original potential control groups individually. Yeah, so for instance, in like a 2010 JASA paper, the Journal of the American Statistical Association, very good journal. These authors, they studied the effect of like a change in the tobacco control laws in California. Yeah, so, and again, what I already said, there's no other state that matches California exactly. And then they simply take all the other states, they apply the synthetic control method, and they find the synthetic California. And the two Californias are then shown to move pretty in parallel before the treatment, and then only after the treatment takes place, right? The synthetic California changes that way, and the actual California changes in another way. Yeah, so actually, you see the pictures here. Here we have the California development, and here we have like the average of all the other states in the US. You see that there is like no parallel trends before the treatment, and of course then, well, whatever happens after the treatment doesn't give you any information because they were already non-parallel before the treatment. And now let's compare this with the synthetic control. Yeah, you see here now kind of both lines, they are really, 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 really close, yeah, before the treatment takes place. And then after the treatment takes place, you see like this divergence here. Yeah, so it seems like the synthetic control really matches California pretty well. Yeah, so it looks like a magic bullet, and indeed, it has many advantages. However, if you do a synthetic control paper, there's many other things that you should kind of take into account because, like, for instance, inference works differently, yeah? But that's just as a remark. Yeah, and then a final thing that I wanted to say about differences is another, let's say, a warning, right? You will see that in the literature, there have been plenty of papers that did simply differences when actually there's variation in treatment timing. Yeah, so kind of like the treatment allocation is staggered. So for instance, group 1 gets the treatment in time period 1, group 2 gets it in time period 5, group 3 gets the treatment in time period 2, and so on and so forth. Yeah? So for instance, let's say kind of again, we have the US states. There is a change in law that first takes place in New York. Then it's taken in Massachusetts. Then the next ones that adopt the law are the Californians, for instance. Yeah. So the treatment takes place in different times. And well, because people thought, well, we understand linear regression so well, what could go wrong, right? Now, the intuition, what could go wrong is that individuals that already received the treatments, they actually act as controls for individuals that get the treatment at a later stage. And this may bias your results. And moreover, kind of if you run this two-way fixed effects model that we always use, then kind of the final estimates that you get is some weighted estimate. Yeah, we will talk about this in more detail in the next slide. And the weights sometimes don't make sense. Yeah, for instance, the weights can be negative, and moreover, kind of what is concerning is that some groups have a larger weight than other groups. Yeah, so kind of like the ATE that you get, the estimate that you get, is not necessarily a representation of the average effect post-treatment. Yeah. Okay, so again, we have this model here, two-way fixed effects. And the dummy is 1 if individual I has received treatment in period T. Yeah? And of course, like, you know, a certain individual may receive treatment in period 2 or 5 or 7, right? Maybe completely different across individuals. So there have been a couple of papers on this issue. And for instance, Goodman-Bakeman shows that the overall treatment effect, yeah, so your beta hat will be a weighted average of all possible vanilla 2 times 2 differentive estimates. Yeah, so again, the same individual can be both in the treatment and in the control group, depending on which group you compare it to. Now, the parallel trends assumption that is necessary for consistency is consequently also a weighted average of the pairwise parallel trends assumption. Yeah, so and if you have one group where the pairwise parallel trends assumption is violated and that group gets a lot of weight, then of course your overall estimate happens to be biased. You know? So here's the issue, kind of like if you have differences in treatment timing and you have difference of the treatment effect across groups. Yeah, because the overall estimate is a weighted average. If there's some group that has a large weight and that kind of where the treatment effect differs a lot from the others, then this may bias your overall estimate. Yeah, so it may not be represented for the post-treatment effect. Yeah? Okay, so here's kind of like the example that Goodman-Bakeman gives. So kind of we have 3 groups. So first of all, we have like this untreated group, that's the green line, never receives treatment. Then we have like the ones that get the treatment early, that's red line, and those that get it late, the blue line. And we assume that the treatment has a positive effect. Yeah, and actually it also has a different effect. So here the treatment effect is a little bit smaller than here. And the overall treatment effect can be obtained by basically averaging all these effects. Yeah, so kind of like here we have like early versus untreated. Here we have late versus untreated. Here we have early versus late. And here we have late versus early, right? So you see, here in this particular case, this would be the treatment group, the blue line, and the red line would now be the control. And you see kind of what happens here. These red guys, they have received treatment already. So you have to kind of be a little bit careful how you evaluate this overall. So this is kind of a warning. You have to be a little bit careful when there's variation in treatment timing. Nowadays, there exist packages in Stata, for instance, that do some fancy computation. It's written by these guys here. Yeah. So if you find a paper where you have staggered treatment, that's an alternative. And I think that's pretty much it for the regression, for difference and differences. And we do regression discontinuity in the next part.